Thank you very much. So it's a great pleasure for me to be here and to give this morning lecture. Many thanks to the organizer, Rafael and Sharka, for organizing not only that meeting, but so regularly these beautiful meetings. This is a lot of work, I know, but this is very useful to the community. So I'll speak a little bit about interaction of vortices in two-dimensional viscous flows. This is a subject I've been interested in since 10 or 15 years. I didn't make much progress, I must say, but thanks to new people coming into the field, there have been some developments recently, and maybe it's time to give an account on that, okay? It's a subject which is, I find interesting. It's not too difficult, not completely trivial, and it's a lot of fun. Okay, so why are we interested in the interaction of vortices? Because this is very important in the dynamics of two-dimensional viscous flows. And let me show you, if I can, a little movie to convince you. This is a movie stolen from the internet, right? So let me start it again here. This is a numerical simulation of the two-dimensional vorticity equation in a square box with periodic boundary conditions, okay? There is no forcing in the equation. All the energy is in the initial data. The initial data is some random distribution of vorticity. What you see here on the movie in red are regions of large positive vorticity, and in blue, these are regions of large negative vorticity. And if you run the movie, you see that after some transient period where the motion is very complicated, very rapidly the motion organizes itself as a collection of vortices. You have blue vortices which rotates clockwise, and red vortices which rotate counterclockwise, and you see that, okay, vortices of the same color may merge, whereas vortices of opposite color don't. And the longer you wait, the fewer vortices you observe, which are larger and larger, and this is compatible with the general picture of the two-dimensional inverse energy cascade. So this is just to say we are interested about vortex interactions, because vortex interaction and mergers are the key phenomena for two-dimensional freely decaying turbulence. Two-dimensional freely decaying turbulence is all about vortex interaction and vortex mergers, so if you can understand something from that, then you understand something from the dynamics. Let me try to go back to the main slides here. This was the technical part. Okay, good. So what do we understand about vortex interactions? Well, to make a long story short, we understand mainly the weak interaction regime where the vortices are widely separated. If you assume that the distance between the vortex centers is large compared to the typical size of the vortex cores, then you have some kind of weak interaction regime in which you can approximate the vortices by point vortices, and then you are reduced to an ODE system for the positions of the point vortices, and this is the celebrated the point vortex system. So in the first part of my talk, I will recall some basic facts about the point vortex system, its relation with the fundamental equation of fluid mechanics, and I'll review the solution of that system in some very particular cases. And then in the second part, I will consider the Navier-Stokes evolution, starting with vortices initial data, and I'll focus on the particular case of a viscous vortex dipole where you have only two vortices with opposite circulation. In that case, the motion is very simple, but the game is to follow the solution of the Navier-Stokes equation as long as possible, okay? And the third part of my talk, which may be reduced to zero, will be some sketch of the proof of the result I will state in the second part. Okay, good. So let me recall what the point vortex system is, and let me just recall what a point vortex is. A point vortex is a vorticity distribution which is just a Dirac mass located somewhere. I put some coefficient to have something which is dimensionally consistent, because the coefficient gamma here is a unit of length squared divided by time, so that this is really 1/time. This is a vorticity distribution. So the corresponding velocity field that you obtained, it depends on the geometry you are working on. I will be in the whole plane R2, so where it's very simple, but you can also consider point vortices in other geometries, like on the sphere, if you're interested in planets, or on the torus, like in the numerical simulation. You will get different formulas, but for me, it will just be gamma over 2 pi, x perp over modulus of x squared. So this means that the streamlines are concentric circle here centered at the origin, and along these circles here, the velocity is 1 over the distance to the origin. This is just a point vortex, okay? So if you have only one point vortex, nothing happens. I mean, it stays where it is. This is very sad, okay? But if you have several ones, then you can write an evolution equation, which is the point vortex system. So you assume that you have in the plane some place denoted Z1, a point vortex with circulation gamma 1, at another place Z2, a point vortex with circulation gamma 2, and you have n of them. So you have Zn here, maybe, with a circulation gamma n. And then you write an ODE system for the position Zi of these vortices by just postulating that each vortex is advected by the velocity created by the other point vortices. So at point 1, you compute the sum of all velocities of all other vortices, you sum of them, and you decide that this is the velocity of your point vortex. So this gives you the system of ODE, dzi over dt is equal to sum of j different from I, gamma j over 2 pi. This is basically this formula, zi minus zj perp over zi minus zj modulus square. Okay, you take this in an ordinary system of ordinary differential equation for the position zi to zn. The gamma 1 to gamma n are fixed parameters of the problem. This is the celebrated point vortex system, which was considered already in the second half of the 19th century. It was written by Helmholtz, studied by Kirchhoff, and the first mathematical work on it is the thesis of Walter Gröbli, which was published in 1877. Okay. Now, okay, this is the point vortex system. This is just one slide about what is the relation between the point vortex system on the one hand and the fundamental equation of fluid motion. This will deserve more than one slide, by the way, but this is just to have something here. So this is the two-dimensional vorticity equation, okay. The two-dimensional fluid is given by a velocity field u, in R2. I take omega to be dx1 u2 minus dx2 u1, which is just the two-dimensional vorticity, which is a scalar, and this satisfies this very famous equation, dt omega plus u dot grad omega is equal to nu Laplacian of omega. Nu is the kinematic viscosity. If you consider Euler, nu is equal to 0, otherwise nu is strictly positive, and this is Navier-Stokes, okay. So the problem is that the justification of the point vortex system is not completely straightforward from the fundamental equations of fluid mechanics, because you cannot just, for instance, take initial data, which is a collection of point vortices, so you say omega 0 to be sum from I, from 1 to n of gamma I Dirac mass located at points x, y, for instance. This is a collection of point vortices, but you cannot take this as initial data for the two-dimensional Euler, or at least I cannot do it, okay? So this is too singular to solve the Euler equation. I mean, the solution of Euler equation with those initial data is not defined in any functional framework I know of, okay? So you have to cheat a little bit. So the idea is that instead of starting with initial data which are really point masses, you consider some vortex blobs, okay? This is the same, they are located near some points, x1, x2, xn, but they are no longer Dirac masses, they have some support, some size, epsilon, it's a vortex blob. If you do that, and this was done by Marchioro and Pulvirenti, also by Turkington in the 80s, you can prove that if you start with a collection of vortex blob which is epsilon concentrated along some points, and have circulation gamma 1 to gamma n and so on, and if you solve the Euler equation, which then is well defined, the situation remains the same at a later time. You still have vortex blob which are well identified, but they have moved to leading order according to the solution of the point vortex system. If you start with vortex blob of size epsilon, maybe you go to 2 epsilon or epsilon, the square root of epsilon or something like that. They become a little bit larger, but qualitatively you have the same picture. So by an approximation procedure, you can give a rigorous derivation of the point vortex system from the Euler equation. Okay, so there have been recent improvement in this direction by Buta and Marchioro, improving a little bit the time, some rewriting by Cecchi and Zeiss, and some different but related work by Davila, Del Pino, Musso, and Wei, where they consider more specific initial data, but they also have some more detailed information on the solution. Okay. Now it's also possible to start from the Navier-Stokes equation. Whether you prefer Euler or Navier-Stokes is a matter of taste, right? Okay? So suppose that you are married with Navier-Stokes equation. You want a justification in the framework of Navier-Stokes equation. So you can do the same, consider vortex blob as initial data, solving the equation, but then the viscosity is your enemy because it spreads the blobs. So you have to assume that the viscosity is sufficiently small compared to the size of your vortex blobs. If you do that, this was done by Marchioro in the 90s, you get a derivation of the point vortex system. But there is also a simpler solution, which I want to advertise because this is my work, okay, long time ago, is that for the Navier-Stokes equation, it's perfectly possible to start with point vortices as initial data. For Euler, it's not possible, but Navier-Stokes has a regularizing term, so you can solve the Cauchy problem for more initial data, and in particular, you can solve for point vortices as initial data. So this is what I call the viscous n-vortex solution. Very simple problem to state. You choose n points in R2, which are pairwise distinct. These are the initial positions of the point vortices. You consider fixed circulations, which are the parameter of the problem. And you consider the initial data, which is just the superposition I wrote on the blackboard here, sum of gamma I Dirac mass at xi. And you take this as initial data for the Navier-Stokes equation. You also assume, and this is a strange assumption, that the point vortex system with this initial data is well posed on the time interval 0 capital T. I should have mentioned, but I didn't discuss this in full length, that the point vortex system here, strangely enough, is not globally well posed for all initial data. This is strange because Euler, 2D Euler or 2D Navier-Stokes equation are well posed, but this system, which is extracted from them and is supposed to be simpler, is not globally well posed for all initial data. It was discovered by Gröbli in 1877 that there are configurations. I mean, if you have at least 3 vortices and they do not have all the same sign and blah, 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 under some condition, you can cook up initial data, which are exceptional, but which leads to a collision of 3 vortices in finite time. Okay, if this happens, I cannot do anything with the rigorous analysis, so I have to assume in my theorem that on 0 capital T, the point vortex system is well posed. For most initial data, this is not a restriction. I can take T to be arbitrary, but for some specific initial data, I have to take T smaller than the first collision time. Okay. So, okay, on the interval 0 capital T, I solve the Navier-Stokes equation. So it's known, it has been known since more than 20 years now that there is a unique global solution of the 2D Navier-Stokes equation with such initial data. This is at the boundary of what we can, at the borderline of what we can do for the Cauchy problem, but this is possible. And you take this solution, which I denote by omega nu, and you take the vanishing viscosity limit. And the vanishing viscosity limit is just a collection of point vortices which moves according to the point vortex system. So this is a very clean derivation of the point vortex system. You start with point vortices as initial data, you solve Navier-Stokes, you take the vanishing viscosity limit, and you discover that you follow the trajectories of the point vortex system. Good. Now, in fact, we can do a little bit better than that because for Navier-Stokes, we can solve explicitly what happens for one vortex. I mean, again, if omega 0 is gamma times delta at the origin, the Dirac mass at the origin, then the solution is known. It's omega nu of xt is gamma over 4 pi nu t e to the minus x squared over nu t. This is just the solution of the heat equation, fundamental solution of the heat equation, but in fluid mechanics, it's called the Lamb-Ozane vortex. It has a noble name, but okay, it's just the heat solution of the heat equation. And if you are interested in the velocity field, you can compute it too. It's something like gamma over 2 pi x perp over x squared. This is just the point vortex, but then it's regularized near the origin by nu t. There is a 4 maybe. Okay, good. So this, okay, so if you have only one point vortex, it becomes a self-similar Lamb-Ozane vortices. Now, what happens to a collection of vortices? Well, we can guess what happens. These vortices will move according to the solution of the point vortex system, and they will not stay point vortices, they will become to leading order Lamb-Ozane vortices. So the ansatz for an approximate solution is extremely transparent. you approximate the Navier-Stokes solution by a collection of Auxane vortices which are located not at the initial position, but at the time-dependent positions that you obtain by solving the point vortex system. Okay? So this is the improved formulation of the result, which is here. So the assumptions are the same. You solve the Navier-Stokes equation with point vortices as initial data. And the conclusion is much stronger. I claim that the solution at time t can be decomposed as a superposition of vortex blobs. And each of these vortex blobs is a self-similar solution, if you want. It depends on time. So this is a self-similar ansatz, gamma I over nu t, wi of x minus zi of t over square root of nu t. So this is just an Lamb-Auxane vortex located at position zi of t, and the profile is not exactly the Gaussian. If the profile was exactly the Gaussian, this would be exactly a superposition of Lamb-Auxane vortices, but the theorem says you that the profile, I mean the self-similar profile of your vortex blob stays close to the Gaussian, and you can measure the difference. It's controlled by nu t over d square, and d is the distance between the vortices, nu is the viscosity, so for fixed time as nu goes to 0, this is very small. So this tells you that you can control the solution of the Navier-Stokes equation by a superposition of Lamb-Auxane vortices, the center of which follow the trajectory given by the point vortex system. Okay. So this is true for any configuration of vortices, and this is true for any fixed time, provided that the point vortex system is well defined. Okay. Now we may ask, is it possible, suppose that the solution of the point vortex system is global in time, this happens often, okay? Can we do something for longer time? Can we follow the dynamics not for a fixed time, but for a time that becomes longer and longer as the viscosity goes to 0, for instance? And this is not written yet. I mean, if you look at the proof of my result 15 years ago and follow really the estimates, you can get some little improvement. So the time of control is not fixed, but could increase like logarithm of 1 over nu as nu goes to infinity, but in general it's impossible to do better than that. Okay. Now in the rest of the talk I will consider some very specific, very simple initial configuration, not a general configuration of vortices, but configuration where you have only two vortices. Okay. These are vortex pairs. So for vortex pairs, this has been known since, I mean, the 19th century. There are two interesting cases. The first one, if you have a pair of opposite circulation, so a negative vortex with circulation minus gamma and a positive vortex with circulation plus gamma, then the pair is just uniformly translating downwards with a velocity which is gamma over 2 pi, the distance between the vortices. Okay, so this is uniform translation. If you have two vortices of the same circulation, this is uniform rotation of both vortices around the common vorticity center, and you see this behavior appearing in the movie I showed you, okay? And if you have unequal vortex pairs, you can always compute it's also uniform rotation about some vortex center. So toy models for the interaction of vortices are vortex pairs, either the dipole here or the co-rotating pair where you have either translation of rotation. These are of course global motions, and in that situation you may like to control the solution of the Euler or the Navier-Stokes equation for a longer time than just a fixed time. Okay. You also have some very nice picture for the streamlines in this situation, but I will not have time to discuss this, so let me skip that. Just some numerical simulation, not from me, these are old ones by the way, about what is the long time behavior of the solution, I mean observed physically in both situations. So in the case of a vortex dipole, so this is a negative vortex and a positive vortex, so I recall this pair goes downwards with constant velocity. This is a numerical simulation where you follow the motion of the vortex pair, so it looks like a stationary state. This is initial time, so this is well separated. Then it starts growing because of diffusion, okay? They start interacting, so this becomes non-radially, this is still close to radially symmetric, but this is not. And the longer you wait, the stronger is the deformation. You even create a tail, which becomes very, very long. And if you look at a very long time, t is equal to 1000 here, you see that you form a dipole which is no longer separated, but there is no real merger. They do not merge. and you have a long tail which is not indicated, but it will go above the ceiling here, okay? So this is what happens. So this is the fate of vortex, a viscous vortex dipole. There is no merging, but it forms sort of an interacting dipole which travels slower and slower because this mixing here eventually cancels the translation motion. For the rotating pair, the scenario is much more dramatic. You have this merger phenomenon that you have seen on the movie, and I cannot refrain trying to show you a movie of an experiment. Oh, I'm not allowed to show it. I didn't try this, so sorry. Okay, I'll not do it then. So there are very beautiful experiments made here in Marseille by Patrice Meunier, not in Lumini, but in another department in Marseille, where you have experiments where you see the merger of this, and you see that the evolution is much more dramatic. So the vortex merger is the most terrible nonlinear phenomenon that can happen to a vortex pair. I mean, if you are able to understand that, then we'll make a very big progress, but for the moment it's completely impossible to describe mathematically. Okay, so this was the end of my long introduction, and now I will focus from the rest of the talk just on the case of the very simple case of a viscous vortex dipole. So let me start again from the beginning. You consider initial data for the Navier-Stokes equation where you have two vortices. You have a vortices of circulation gamma is positive, located at the place minus d/2, 0, and a vortex of negative circulation minus gamma, located at the position d/2, 0. I put the positive vortex here and the negative one because I want the vortex pair to go upwards. I don't know why, I'm not satisfied with something going downwards. So I prefer having a positive vertical speed. Okay, good. So this vortex pair will travel according to the point vortex system, which a constant speed u, which is gamma over 2 pi d. D is the distance between both vortices. Okay. And I want to control the solution of the Navier-Stokes equation in that situation. There is a unique global solution for any value of the viscosity. I'm just asking the question, what is the behavior of this solution for a long time? Okay, good. Now, this solution is very simple, not only because the vortex motion is simple, I mean, it's just a uniform translation. If you go to a moving frame, this will be like an equilibrium. But there is also a symmetry. I mean, initially, the vorticity is odd with respect to the horizontal variable, okay? Which means that omega of x1, x2, t is minus omega of minus x1, x2, and t. And this symmetry is preserved by the Navier-Stokes evolution. So for all times, this vortex is the mirror image of this vortex by odd symmetry, which means that I have to compute only one vortex. If I compute one vortex, I get the other one just by symmetry. So I just reduce the motion to the study of a single vortex which is close to equilibrium. So it looks like a tractable problem, right? We are really not expecting some very wild dynamics, okay? Now, where is the vortex located? Well, it is located at a position z of t, which will depend on t. And in fact, z of t can be chosen as d/2 z2 of t. So the vortex will move on a vertical line. There is no canonical definition of the center of a viscous vortex. This is a source of confusion in the literature. You can have several definitions, okay? I take as a definition the center of vorticity. I mean, the blob that I have here has a definite sign, so there are a definite center of vorticity. And if I do that, I observe that due to a conservation of the first order moment for Navier-Stokes equation, this stays on a vertical line. So the center of vorticity will not change. Even in the numerical simulation I showed you, the center of vorticity remains on the same vertical line. But I don't know about the vertical position. The vertical position to leading order is expected to be given by the prediction of the point vortex system, but maybe there will be correction to that, I don't know. So this is not decided by any symmetry of the equation. So my z of t will be d/2 and a z2 of t, which I don't know of, okay? So this is the initial data I consider, okay? And now comes the analysis. So let me try to explain this. This is not so frightening. So what do we do? Okay. we are considering this vortex. This vortex is located here, not at the center of the coordinates, and the typical size at time t is the diffusion length, which is square root of nu t. We have seen here the typical size of this Gaussian blob is square root of nu t, which is the diffusion length. So it's obvious that I have to make a change of coordinates. My coordinates are located here, which is nowhere between in the middle point between the vortices, and the unit length is not the correct one. So I have to introduce new coordinates. The new origin of the coordinates will be the location of the right vortex, and the length scale of my new coordinate should be the diffusion length, so that I can see something at order 1 in space. Okay, so this is exactly this self-similar ansatz here. So please pay attention only to the first line. The other one are just deduced automatically. So I write omega of xt as a vortex of circulation minus gamma. Why minus gamma? Because I chose here to have circulation minus gamma, sorry. So it's minus gamma over nu t times some new function capital omega of x minus z of t over square root of nu t. So this is a self-similar variable which is located at z of t and which has unit length which is square root of nu t. And this is not an exact solution, so it depends also on t. And the other term is just the mirror vortex. I write one vortex and the other one is obtained by symmetry. And the two other lines are just exactly the same, except that this is for the velocity and this is for the stream function if you need it, okay? So this is all automatic. When you have the first line, you have the other two lines, and the Biot-Savart law is completely unchanged. I mean, V is gradient pair of psi, where Laplacian psi is equal to omega. This is all scale invariant. So the only thing we do is to write small omega, which is my vorticity distribution, as a new function, capital omega, which is written in the new variable. Okay, good. And then I have very important notation that I put here. So I will denote by xi my new self-similar variable. So from now on, the space variable will be xi. It's no longer x. X will disappear. Now I'm the world where my variable xi measures the distance to the vortex centers in the unit of the diffusion length. Some parameters, square root of nu t over d, will appear a lot of time. Square root of nu t is the diffusion length, and d is the distance between the vortices. My whole analysis will be in the weak interaction regime where this epsilon is small. The size of the vortices should be small compared to the distance. If this is of order 1, this is when the vortex pair is completely mixing. This is the end of my analysis. So epsilon of t is a time-dependent aspect ratio, and this is my expansion parameter. There is another interesting parameter, which is nu over gamma. The kinematic viscosity nu and the circulation gamma of the vortex have exactly the same physical length, okay? So the ratio is a dimensionless number, and this plays the role of the inverse Reynolds number. So I have to go to large Reynolds number, which means that the convection effect, the convective effect are much larger than the diffusive effect, and this corresponds to this delta to be very small, okay? And finally, they have the advection time, d square over gamma. D square over gamma, I mean, if I put a 2 pi here, 2 pi d square over gamma is exactly the time needed for the inviscid vortex pair to travel a distance which is equal to the distance between the vortices, okay? So they have distance d, and I wait until they travel vertically over a distance d also. So it's a unit length on which the inviscid motion is really occurring, okay? So it's obvious that I will have to conduct an analysis which is on a time interval which is large compared to this one. Otherwise, I don't see any motion, okay? So this is very important notation, so maybe I should write it on the blackboard, and fortunately, this is already here. Okay, good. So these are these parameters here. So now, okay, the only thing I do now is to study the equation satisfied by the new profile capital omega, okay? So I just take the vorticity equation and I rewrite it in terms of the new variable capital omega. So I'll go very slowly here, because if I lose you here, then of course it's finished. But this equation is just the same as the original vorticity equation. So let me go back to the original vorticity equation, which is unfortunately far away here. So you had dt omega plus advection term is equal to diffusion term. The new equation will be exactly the same with some little modifications. So let me explain you what the new equation here. Here it is. So the time derivative becomes t dt omega. This is due to self-similar variable. Everything here is dimensionless, so I cannot have dt. So it's t dt, which is sort of dimensionless version of the time derivative. So this is the time evolution. The diffusion operator becomes this operator here. This is very, very familiar. As soon as you go to self-similar variable, the Laplacian is modified by you add the dilation operator and a constant. This you see in all self-similar ansatz. So this is due to the diffusive part. So this is what becomes from the heat equation. T dt omega is equal to L times omega. Then you have the nonlinear terms, and they have 1 over delta. But 1 over delta, recall you, it's the Reynolds number, okay? So the Reynolds number comes into the factor of the nonlinear terms in Navier-Stokes equation. As soon as you write the Navier-Stokes equation in dimensionless coordinates, you have the Reynolds number, which comes as a factor in front of the convective term. So this is what we have here, of course. V dot grad omega is just the advection term. Omega is advected by the velocity v, field v, that it creates by the Biot-Savart law. Okay. Now, this is the mirror vortex. This is sort of a translation reflection operator. I mean, my new coordinate, if I'm sitting on the vortex on the right, the other vortex is at distance minus 1 over epsilon, at distance 1 over epsilon in the negative direction. So when epsilon goes to 0, initially the other vortex is at infinity in my new coordinates compared to the diffusion length. So this is, so you are advected by the velocity field of yourself and of the mirror vortex. And what is this term? Well, this term is just because I went to some moving frame here with some unspecified velocity z of t, okay? So of course you have advection by the velocity of the moving point here, okay? So this term, if you go to a moving frame, you generate an advection term which involves the speed of your moving frame. This you have always. So this term is not a bad one because z dot of t will be chosen so as to compensate partly for this term, and this is how you determine the vertical velocity speed. Okay. Okay, so this is just to convince that you have exactly the same equation as before. Diffusion, advection by the mirror vortex, and this additional term due to the fact that you are in a moving frame. And we'll have to study the solution of this equation. Question, with which initial data? You cannot choose your initial data because it is not a regular Cauchy problem at t is equal to 0. When you say t, when you put brutally t equal to 0 in this equation, what do you get? T dt goes to 0. You have L omega, maybe I can write this on the blackboard here. So if you set brutally t equal to 0, you obtain 0 is equal to L omega plus 1 over delta v dot grad omega, and that's it, okay? Because the other terms go to 0, epsilon is 0 initially, so this term is gone, and this term is just a translation at infinity, is also 0, at least formally, okay? So you obtain that the initial data, omega 0, should satisfy this constraint. But if you assume that omega has integral equal to 1, okay, maybe I can write this as a little bit more carefully. So my initial data should satisfy v0 dot grad omega 0, and I also want that omega 0 d psi is equal to 1. If you impose that, there is only one solution to this equation. This has been known for a long time, which is just the Gaussian, which is written here, which is the profile of the self-similar Lamb-Ozane vortex. You solve, I mean, you are not really solving a Cauchy problem. You start from Dirac masses, and the fundamental solution of the heat equation produces you this self-similar Lamb-Ozane vortex. You cannot avoid that. So this, you have to solve with this initial data, which is just in self-similar coordinate, the Lamb-Ozane vortex. So it's very clear. Now you have this evolution equation, which is ill-posed at t is equal to 0, but you have to solve from this very specific initial data, and you have a unique global solution, and you want to study this solution. Okay? Good. So unfortunately, this is not so easy, but maybe I will explain the difficulties later, and I state the result now. So this is the main result, okay? It regards the evolution of this solution with this initial data, okay? So if the Reynolds number is sufficiently large, so the inverse Reynolds number delta is sufficiently small, you can control your solution omega of t. Omega of t will be close to omega at 0, which is the Gaussian, with a bound epsilon square, an error of epsilon square. Epsilon square is nu t over d square, okay? Over a very long time interval. So t0, I recall, is my advection time. This is a time on which I see an evolution of the motion given by the point vortex system. And now you see that I can go to time t0 times delta to minus sigma for any sigma less than 1. So I want to explain this on some little picture here, maybe, to see what's here. So I have my vortex pair here initially. Let me try to make the picture like that. I have my vortex pair. Here I have a plus gamma, and here I have minus gamma. And vertically, I have the vertical axis, but it's also the time, because the vortex pair is traveling upwards. So the first time here, so let me here, this is the time axis. So this is t is equal to 0. These are my initial data. Now, when you are here, you have traveled a distance which is compared to the distance between the vortices. This is what I call the advection time, t0. This is the minimal time I want to reach. Otherwise, I don't see any motion. Now, and this was d square over gamma, okay? Now I have another time here, which is d square over nu. This is again a time, and d square over nu is epsilon is equal to 1. When the time is equal to d square over nu, this epsilon is equal to 1. This is the time where the vortices are so large that their size is comparable to their distance. I call this the diffusion time, so this will be the advection time, and this will be the diffusion time. When you reach the diffusion time, no way you can continue because the pair is completely destroyed by diffusion, okay? Now the assumption that the Reynolds number is large or the delta is small is saying that this diffusion time is much greater than the advection time. You move a long distance until you are destroyed by diffusion. In the converse regime, if you start with a small Reynolds number, it means that the pair is destroyed by diffusion without having time to move. This is not the regime we want to consider. So we would like to reach this term here, which is t0 divided by delta. This we cannot do, okay? It's much beyond the scope of the analysis, but we can go interpolate between this one, and we can go to t0 delta to the minus sigma for any sigma less than 1, okay? So we are nearly reaching the optimal time. If sigma was equal to 1, the result will be nonsense. We cannot go to this state here, but we can go almost to this time scale. So this is a very, very long time scale, and the vortex pair travels a very long way, hence my title, until it's destroyed by diffusion. Okay. Okay, so the statement is this one, so I can control the solution with some error over a very long time interval. And the norm here I should not comment, but it's a very strong norm, which in particular implies the L1 control, but it's much stronger than this. Okay. Good, so this is the main result I wanted to say. So it's possible here to follow the vortex pair over a very, very long time. Okay. Now I think, okay, this is a slide where I should just mention all things that I am ignoring here. It's that vortex pairs can also be studied from different point of view. I chose to study the solution of the Navier-Stokes equation with point vortices as initial data because it is my taste. But you can also, for Euler, construct exact solutions which are uniformly translating. These are called vortex pairs, also for vortex dipoles for Euler equation. So this was done by Turkington in the 80s and also by Burton. There are recent progress by a group of Chinese mathematicians around Daomin Cao in Beijing. They also the group in Bath doing some recent progress on that. So a lot of exact traveling wave solution of Euler I know are known, which look like a vortex pair. These are very special solutions because if you take just arbitrary initial data, you don't get a traveling wave solution, but you can construct them. And there is also a very strong group now, some distinguished members are in the audience, doing the same thing for vortex patches, not only for vortex pairs, but even much more complicated dynamics. So from the Euler, there are corresponding works which go even infinity in time, because these are traveling wave solutions, which can be constructed for the Euler equation by, say, variational or perturbation methods. Okay, I will not mention that at all. I'm doing just here the viscous case, for which you cannot go to infinite time, of course. The infinite time is, the pair is destroyed, but you can go to a very long time depending on the viscosity parameter. Okay, good. Okay, so now it's the last part of my talk, so this will be more complicated, so I will speed up a little bit. It's just to give you a flavor of the proof and to show you why this is not so easy. I mean, for the moment everything was easy. I just say you solve the Navier-Stokes equation and do. But the problem is where? The problem is that this equation here is very bad. It's very bad because you have 1 over delta in front of the nonlinear terms, and delta you have to do an analysis that is uniform in delta as delta goes to 0, because basically I don't take really the limit as delta goes to 0, but I want delta to be as small as I want. It's a fixed parameter, but can be as small as I want, and all my estimates should be independent of delta. This is not a very good start if I have delta in 1 over delta in front of the nonlinear term. So this equation is extremely singular. So if you try to solve it by a fixed point argument out of the initial data, you are dead. You have 1 over delta in terms of the terms that you want. So you can solve it for a time of the order of delta, but certainly not for a time that is order 1. Okay. So I have a big problem here. And the solution for this problem, like in boundary layers theory, is well known. You first have to construct a very accurate approximate solution of the problem, and then you will look for an equation for the correction. So the first step, which is well known, is the construction of, no, I'm going in the wrong direction. Sorry. Is constructing an approximate solution. So omega 0 is my initial data. I construct an approximate solution, so it will not satisfy exactly the equation that I wrote here, but it will satisfy the equation up to an error which will be smaller and smaller the higher approximation I take, okay? So omega, so it will be a power series in epsilon. Epsilon is a time-dependent parameter, but for fixed time, this is just a parameter, and I expand in the power of this parameter here. So this will be time-dependent because epsilon is time-dependent. It's a power series in epsilon, but the order epsilon term is missing. It's not in epsilon squared. They have epsilon cube, 4, 5, but just the order epsilon is missing. This is because I chose the vertical velocity of the vortex pair in such a way as to compensate for the first term. So it starts at epsilon, and for the vortex, the velocity, you have a similar expansion. And then the idea is very clear. You plug into the equation, you look at order by order in epsilon, and you try to solve and determine omega 0 is known, this is the Gaussian, and you have to determine omega 2, omega 3, and so on. We need up to omega 4 to start with, but to obtain this result here, you will have to go to very high order asymptotic expansion. Okay. So, I don't want to enter technicalities, but just one slide. When doing the construction of the approximate solution, 2 linear operators appear. The first one you know already, this is this diffusion operator, sort of a Fokker-Planck operator. This one comes. And the other one, which I call lambda, is the linearization of the nonlinearity in the Euler equation at the Lamb-Ozane vortex. Everything is close to the Lamb-Ozane vortex, so you have the term u dot grad omega, you linearize it at the Lamb-Ozane vortex, and you obtain this operator lambda, which is formally skew-symmetric. And if you look at all this in a Gaussian weighted space, here an L2 space with a Gaussian weight, you have this beautiful result, which has been known in part since a long time, which tells you that in this space, the diffusion operator is self-adjoint with purely discrete spectrum, eigenvalues being 0, -1.5, -1, and so on. This is in fact the harmonic oscillator. And the same space, the operator lambda is skew-symmetric, and it has an infinite dimensional kernel. The kernel is made of all radially symmetric functions plus the first order derivative of the profile omega 0, which is my Gaussian. So this information has to be used when you construct. I mean, I will not go into the details, but you need this information on these operators when you try to construct order by order your asymptotic expansion. So let me give you an example. What is the second order corrector? I mean, you have omega 0, omega 1 is 0, so I need to contract omega 2. When you plug into the equation, you trust me that I know how to do this calculation, you equal all the terms of the same power of epsilon, you obtain this elliptic equation. Delta times 1 minus L, this is the diffusion equation, minus lambda acting on your unknown omega 2 is equal to something that you know. Okay? So you have to invert this linear operator. This is good because from the theorem I just mentioned, this operator for delta positive is always invertible. The only problem is that the inverse is 1 over delta, the norm. And this you don't know, I mean, you have to do something which is uniform in delta. Okay, so let's forget about delta, put delta is equal to 0. Then you see that you have to invert lambda. Is lambda invertible? No. Lambda is a self-adjoint, a skew-symmetric operator with an infinite dimensional kernel. So you have infinitely many solvability conditions if you want to inverse this operator. Your right-hand side should be orthogonal to all radially symmetric functions and also to the first-order derivatives of the Gaussian omega 0. Okay? Now the right-hand side is explicitly known, is something which is indeed orthogonal to radially symmetric functions, so no problem. It's also orthogonal to d1 omega and d2 omega. Okay? So you can invert the operator lambda here, and this is the beginning of a regular solution of this elliptic equation, which can be expanded as a power of delta. So you obtain some formula. Omega 2 of psi is some radially symmetric function which is negative times cos 2 theta. Theta, r and theta are here the polar coordinates for my self-similar variable psi. So you obtain a nice formula for this. So at least omega 2 you can construct. You are lucky because, I mean, you have some conditions to fulfill, but they are fulfilled in that case. Okay. Now you can return to the construction of your approximate solution and consider what you have done. You have done so far a second order approximation for which the leading term is the Gaussian, and then you have this correction here, okay? And this correction accounts for the deformation of the streamlines due to self-interaction. If you have the vortex dipole with, say, a positive and a negative vorticity here, they get deformed in the way indicated in this picture. I mean, the streamlines are no longer circled, they become ellipses, and the major axis of the ellipses in the direction of the propagation. So this is well known by physicists, and this is observed in numerical simulation. Just to mention, for a co-rotating pair where they rotate around each other, the deformation is different. I mean, now the major axis points into the direction of the other vortex center, and this is also well observed in numerical simulation. So this is just obtained from this simple calculation from the second order approximation. Okay, this accounts for the deformation of the vortices. Now, if you have to go to higher order, at each order, let me make a long story short, you obtain some elliptic equation to solve. Okay, and this is the same linear operator in the left-hand side, basically, except that the right-hand side is more complicated and involves all that has been previously constructed. And here you have infinitely many solvability conditions to satisfy at each order, but you can always satisfy them because you have to be orthogonal to all radially symmetric functions, but it's easy to see by some symmetry of the original Euler equation that if you have a part here which is radially symmetric, it has a delta in front. It's always multiplied when delta is equal to 0, which means Euler, the vortices that you have in the pair are in fact odd, even function of the variable x2, which is not the case obviously for Navier-Stokes, but for Euler it's true. So this means that if you have a radially symmetric part, it's multiplied by delta. But for radially symmetric solution, lambda is 0, so you can divide both equations by delta and invert this operator, which is purely elliptic. So this is no problem, okay? And now you have, now you have to just 2 degrees of freedom to cancel. You have to be orthogonal to d1 omega and d2 omega. And this, if this is not the case, you do it by putting corrections to the vertical speed and the horizontal speed of the vortex. So the position of the vortex, the z of t, can be used to satisfy the solvability condition here, and this is how it should be done. So you can construct at all orders. By the way, you obtain in this way some higher order correction to the velocity field of the vortex, and this is very interesting. The velocity of the pair. Z2, I mean, I recall that Z2 is the vertical location of my vortex pair. Z2 prime is gamma over 2 pi d. This is the prediction of the point vortex system. And now you have the leading order correction due to finite size effects. And it occurs at order epsilon to the 4, so quite higher approximation. And it's completely explicit. This formula is also is known since a few years in the physical literature, and it's recovered by this very simple calculation. So you see that the vortex pair goes with uniform speed, but it slows down. I mean, this has a negative sign, so the velocity decreases due to interaction. This is the beginning of a process which eventually will lead to a vortex which is a dipole which is completely steady. Okay? Okay, so you can construct all this. And okay, I will even speed up a little bit more. So you have an approximate solution. Okay? Now I don't want an approximate solution, I want the exact solution of Navier-Stokes. So I do the usual trick. Omega is the approximate solution plus a perturbation. The perturbation has to be very small, so I put a delta in front so that it will be small if my perturbation omega pair stays order of 1. And then I obtain an equation for the perturbation. This equation is of course not simpler than before, so I don't read it, but it's the same structure. T dt is equal diffusion operator, some advection term, some mirror terms, and some remainder. The remainder measures by how much my approximate solution fails to be an exact solution of the problem. Okay? It tells you it's... okay, so you have to solve my equation for the perturbation with 0 initial data, but I have a source term that I can make as small as I want by constructing an approximate solution that is as large as necessary. Okay? So it's like in boundary layers, the same idea. I have a very singular equation, but the source term is very smooth and very small, provided I constructed an approximation that is accurate enough. Okay? Good. But this is not it. I mean, if I just do brutal estimates here, I'm dead immediately because this term is very small. Okay? But here you have linear terms which are multiplied by 1 over delta. The nonlinear term has no 1 over delta factor because I put a delta here. But the linear term, I cannot do anything. So if this linear operator here has eigenvalues, this eigenvalue has unstable eigenvalues. These eigenvalues will have real part like 1 over delta. So I will amplify the perturbation very rapidly. And so in a time of the order of delta, I will dead. Okay? So I have to use the fact that these operators are much better than they look. And this is a long story. I mean, to leading order, this is the operator lambda, which is formally skew-symmetric, so it will drops out. But this is not enough for me. I have to see that this cancels to high order. And this is impossible to do in general, but here there is a miracle here. We use the magic trick of Arnold. So there is an energy functional, which is this one, okay? Some entropy part and some energy part, for which all the terms that I mentioned here, which are bad, give exactly 0 contribution. This is obtained from the variational characterization by Arnold of steady states of 2D Euler equation. I don't have time to explain this in detail, but Arnold's method comes with a recipe to construct a quadratic functional for which is invariant under the evolution of the linearized equation at some steady state. And here we are very close to a steady state of Euler because we have very small viscosity and we are nearly close to one of these traveling Euler pair. So we exploit this to design here a functional, a non-local functional for which all nasty terms in my equation are just 0. Okay? And then it remains to do some Grandval estimates, and if you assume, and this Grandval estimate tells you that the perturbation stays sufficiently small. So finally, I have constructed a solution which I control completely, which is close to the initial data, close to my approximation,
and which is valid until this very long time interval, okay? I have to construct, I mean, my sigma here is a very nasty parameter because if sigma is close to 1, I have to construct an approximation of order m, where m is larger than 3 plus sigma over 1 minus sigma. So if I want sigma to the 0.9 here, I need to construct 40 orders in my approximation. But we can do this to any order, so this works. We can take any sigma here, even close to 1, by a sufficiently approximate solution, sufficiently accurate, we can construct. This functional involves some weight, which has to be carefully chosen. So here's a picture of the weight, but I have absolutely no time to explain. So I'll stop here, and I thank you for your attention. Yeah.